Hey, hey Pickles! Did you know that there's a new material that is rapidly approaching the solar cell efficiency of silicon? Can you guess what type it is? Perovskite cells. They have excellent electronic, optical, and semiconductor properties. Perovskite cells are the way to the future, you know? Don't mind Pickles. I think he's just sad that I'll be leaving here soon. I'm Shane Varner, a senior in chemical engineering from the University at Buffalo, also known as UB, and I'm currently in the REU program for chemical engineering. My interests have always dwelled in molecular dynamics, nanoparticle materials, as well as thermodynamics. And this summer I had the pleasure of working with my postdoc mentor, Dr. Charles Hages, and my faculty member, Ruchin Yang, as well as another graduate student, Calvin Fay, and they all helped me a bunch with this project. My research this time is focused on studying chalcogenide perovskites, which takes the positives of perovskites, such as a high energy conversion efficiency, and it gets rid of the downsides by being more environmentally stable and being composed of abundant and non-toxic elements. More specifically, my goal is to see if barium zirconium sulfide, which can form a perovskite on its own, will remain a perovskite when doping or alloying with tantalum, as predicted with simulation software. If this is possible, this new material would have potential as an N-type semiconductor that might be able to rival silicon. A significant hurdle to making semiconductors is the amount of energy and steps that are needed to process them. Silicon, for example, needs to reach temperatures over 1,400 degrees Celsius in order to start melting. But our group has recently found a new way to make chalcogenide perovskite thin films at temperatures as low as 500 degrees Celsius, which is very significantly lower, and the reaction times are really short, ranging from 5 minutes to just 3 hours. I got a lot of hands-on experiences while working in the lab. The glove box is where most of the magic happens. Since the precursors used to make our materials are sensitive to moisture, it's important to think about each step and make sure your precursors are kept as dry as possible. You have to get creative with how you handle your materials, using blowtorches and vacuums to keep things dry, as well as seal products into ampules. Another highlight was using the XRD machine to find out the phase and composition of the material placed inside. I was able to see how topics taught in my materials science class can be practically applied to research and allowed me to have a much deeper understanding of how an XRD machine worked. And I'd like to give a special thanks to Dr. Hages, Ruchin Yang, the NSF, as well as the SURF and REU program for making this experience possible.